during the past few months, I've been trying to rework the page table handling in Xen to respect the ARM, the architecture, how the page table should be handled. So, yeah, the scope of this talk is about how you should update the page tables on ARM. We're mostly focusing on architectural guarantees. So what will say in this talk is how I see how it should work, but it may, in any case, if there is any problem, if there is any difference between the ARM on my slide, the ARM is the best place. So before going on page table handling, on ARM, then when you have an hypervisor, so with virtualization, you have two stages of page table. So the stage one of page table for guest translation, so it's coming from a virtual address with a different level on going to an intermediate physical address. So this is the physical address viewed by the guest. After that, this physical address will be fed to the stage 2 page table, which is handled by Xen, where it will be translated to a physical address, the host physical address. So this is a two-stage process. So the ARM say that special considerations apply to translation tables updates. What does it mean is in some place, it's the way you update the page tables, you need to use the sequence break before make. So it's a sequence required by the ARM to update the page tables. It's ensures that the page table, every processor sees has the same view of the page tables at a specific time of the just before updating or after, etc. It should always be the same. So why do we care? So page tables are shared. When you run in a guest, the stage 2 page tables is shared between different vCPU. The hypervisor page tables may be shared between different CPUs. So when you do an update, you can't stop all the CPUs. CPUs may still using the page tables, so we have to be careful about how we modify the page tables. If you don't respect the break before make sequence, I would say really bad things could happen. Like it could break coherency of the platform. For instance, you will see corrupted data in the guest. You may see wrong data, and it's very specific to a microarchitecture. So the ARM is very explain how we should do it, how we should update the page table, but it doesn't mean that it could be necessary on every platform. So it might be able to work on a processor, and you move to another version, to another vendor's microarchitecture, and it will break. We've seen already that on some platform with Linux at the beginning of the year. And you could think that, okay, I don't care, I could break the coherency, I may receive a TLB conflict. So the TLB conflict is you may have two entries in the page in the TLB saying, pointing to the same address, and as the TLB is confused, it will send faults to either the guest or the hypervisor. And this TLB conflict is implementation defined. So every vendor, every vendor creating a microarchitecture can decide to do whatever they want, either sending the TLB conflict to the guest or sending the TLB conflict to the hypervisor. Before going through all the page tables updates, I will go define a bit about page tables entry. I guess many people here know about it, but I will go quickly. So the page tables on ARM is between 3 and 4 levels. At each level, you are allowed to do super page mapping, so it's a block mapping rather than having the level 2 and level 3 mapping. For instance, you can have a big block of 1 GB memory, for instance, 2 megabytes, or 4 kilobytes, the granules. ARM is supporting different granules, 4K, 16K, and 64K. In case on Xen, we only support 4K today. We choose 4K mostly because it's the common denominators between everything. Because even if the hypervisor is running 4K, the guest can run any granularities. So each block mapping, so the 1 GB mapping and 2 MB mapping or page descriptor, the 4K, contain different information, for instance, the access permission. So if you want to let the guest or the user space access by read writes, or if you want to disable executions. It also specifies the different type of memory. So for instance, device of normal memory. Device is for memory when you want to access memory related to a guest MMO, to the device, sorry. On normal memory is, for instance, RAM. You can also specify the shareability, so non-shareable, inner shareable, and outer shareable. Cacheability, so if you want the cache to be used, write through, write back. Access flag, contiguous bits, on a non-global bit. I will go explain a bit later about the contiguous bit on non-global bits. On the other side, you've got the TLB entry. So the TLB is a structure which caches the result of the translation table works. So rather than having to do the translation every time you want to access the memory, you can cache in the TLB. Each TLB will contain two main things. It will contain some data from the page descriptor, so like the size, the access, not the access, sorry. The size, the permission access, etc. And it's also tagged by ASID, so per application and per guest. I will go through what means ASID on VMID just after. So one of the things that is allowed on ARM is to be able to indicate, so there is a contiguous bit to be able to indicate if there is multiple entry which is aggregation. For instance, you've got, you can't do a block mapping of 1 GB, but you may have really small mapping, like saying 64K or 32 MB for 4K. So if you know that you have in the memory like 64K, you can create multiple entries in the page tables, but at the end, the TLB can cache only one entry. So you will have performance without having block mapping in the smaller granularity for contiguous regions. When you, for the kernel things, in the case of an operating system, you will usually have page tables per process or per threads. So the ASID, the address space identifier, will it's an identifier which will tell which page is associated to a single address space. So it's always applying for EL1, the kernel, on EL0. And it's also providing, so it allows to changing between different process table without having to do the TLB invalidation, because the TLB contains the address space identifier. Each entry will have the address space identifier on the associated page. On the other side, we have the same thing for virtual machines, because each virtual machine has its own page tables. You need also to be able to context switch between VM without having to invalidating the TLBs. Each VMID has its own ASID, so you don't have to worry about having the same ASID in different VMs. And it's also cached in the TLBs. The last bit that is quite interesting in the page descriptor is the non-global bits. So it's only available for stage 1 page tables. It's used, for instance, if you know that a region of memory will be mapped in all the address space, all the process, like the kernel memory or something like that. So you can say that this is global, and you don't need to invalidate for all the ASID. You can invalidate at every time. So like if you modify a mapping in the kernel, you don't need to invalidate for each process. So break before make. So you need to update the page tables. So as I mentioned, break before make is not. You need to use in some place. You may not need to use everywhere. So you need to use break before make when you change the size of the block. So for instance, when you move from a super page to a table, like you want to shatter a super page, a block, you've got a 1 GB block, and you want to make a 2 MB mapping or a 4K mapping. Or it could be the inverse, like you've got a series of 4K mapping, and you want to create a super page on top of that. And the last thing is when you set or unset the contiguous bit, because it's a contiguous region and you may want to change that. The second thing is when you want to replace an entry in the page table, which can, like if you have a valid entry with an output address and you want to change to another output address, if one of these entries is writable, you need to also using the break before make sequence. Same thing when you change memory type, like when you move from device to normal memory. Cacheability attributes is the same. You may also have to care about the cache in this case. And the last one is when you create global entry, which may overlap to non-global entries. So, for instance, you decide to reallocate memory. That for every process, but in one of the cases, this is already in a process. And there is also a few cases where break before make is not necessary. It's the case when you changing the permission of an entry. So, for instance, in the case of mem access, in Xen, it will be like moving from a read writes to a writes. You don't need to changing this using the break before make, or when you change the access flag in the page tables. So, the key things of break before make is on why it works is TLB are not allowed to hold any translations that generates a translation fault, an address size fault, or an access flag fault. So anything that is not valid is not in the TLB entry. So that's the main things of. I will explain just later on the next slide the sequence, but that's the main points of break before make and why it works. So it's a four-step approach. It's break before make. So what you do is you replace the old entry with an invalid entry. So in the page tables, it's invalid. You invalidate the TLBs by broadcasting the TLBs instructions. So when you will broadcast on each CPU, this TLB won't, the TLB entry won't exist anymore. For that, you need to ensure that the TLB instruction has completed using DSB, the memory barrier, on ISB to flush the pipeline. So you know that after the step 3, there is nothing, there is no TLB entries that cache this entry. And then you write the new entries. So how does it how this sequence makes sure that there is nothing in it? So the first step was the break step. It removed an entry. The step 2, 3, so like sending the TLB invalidations and waiting for the completions, it ensures that all the processors have seen the updates. So before you do any modification on the step 4, the make will just create the new entry and make it visible to everyone. You can see that because of processor may running at the same time, after the step 1 until the step 4, there may have a time when the processor may want to access the entry you modified, but the entry is not here anymore. So you have to make sure that so you will receive a fault from the guest or a fault from the hypervisor. So you need to make sure that any spurious faults needs to be be ignored for the moment. Like you may want to check, like doing some locking serialization to make sure that you don't inject a wrong fault to the guest. Before going through what we need to do on Xen, is there any questions about break before make? In Xen, we use page tables in multiple places. The hypervisor page tables, to handle the memory in Xen, on the stage 2 to protect each guest. Let's start with going through the hypervisor page table. So here is the layout of the ARM32 page table. So you can see that you've got the Xen text a fixed map. So where you want to map something in a specific address. Early boot mapping, like for instance, is for relocating Xen or having the first mapping of the device tree in the memory. Frame table is where where all the page information is cached. The virtual map, the Xen heap and DOM heap. So what's the difference between Xen heap and DOM heap? So the Xen heap is always mapped in the virtual address of Xen. In case of ARM32, it's very usually small because on ARM32 the address space is at most 4 GB, so you may not be able to map all the memory. It's also mostly used for allocating Xen internal memory, like internal structure. On the other side, you've got the DOM heap that is map on demands. So when you use any memory in DOM heap, you have to explicitly say, I want to map this memory, and I have to unmap. On ARM32, the DOM heap is per CPU, so when you map something, you will only map for the current CPUs. You won't map on the other CPUs. If you want to map for all the vCPUs, you will have to use vmap. Those pages are often tied to a specific domain, so it's where we allocate the guest RAM. We allocate the stage 2 page tables also. So when we update the page tables, stage 2, we have to unmap every time. In the case of ARM64, because the virtual address space is really big, 64 bits, we don't have the two. We map all the memory, so we don't have the two heaps. The two heaps are merged in the same place. So you can see the difference on the memory layout. So you still have Xen text, FISMAP, early boot mapping, which is common for ARM64 and ARM32, the vmap, the frame table. Rather than having two heap at the end, we have a 1-1 mapping of 5 terabytes at the end. So every time you want to access the memory, it's just translating the physical address to the virtual address, and you don't have to worry about updating the page tables. So as I mentioned, some mapping in Xen are common between each CPU. Some other mapping are not common, like the DOM heap. So there is few places where the mapping is done at the beginning of Xen, as the boot of Xen is not modified, like the Xen text is mapping once on. It's not modified at all. And there's other places where we have to modify at runtime. So for instance, the DOM heap on ARM32, we have to map unmap every time. But because the DOM heap is specific to a CPU, break before make is not necessary in this case. On the other side, we have a virtual memory that can we can map contiguously page in the virtual memory using the vmap. This is common to all vCPU because when you map it, you use map for a long time. Haven't much looked at the code, but it's where we might need having break before make for the handling the hypervisor page tables. And so the hypervisor page table is quite simple, quite straightforward. In the case of stage 2 page tables, you have to make sure that no one is. So you may have to use break before make in some place. I will just go a bit later. So because when you do a mapping on the stage 2 page table, all the CPU is running usually, because a domain is allowed potentially to map and map some, or to allocate more memory for him, and it will be mapped in stage 2. So we have to consider break before make in two places. When you insert a new mapping, because you may potentially replace an entry that is valid, or when we shatter page tables. So in case of stage 2 page tables, we usually try to allocate as much as possible contiguous memories, like for instance 1 GB, 2 MB, so to avoid having override in the TLB. Because when you do 1 GB super page, you will have only one entry in the TLB. If you do if you shatter the 1 GB in 4K entry, you will have the same number in the page in the TLB. So this is one case where you have to think about updating the page tables. But on the other side, you don't need break before make for mem access operations. So when you want to change the permissions, it's not necessary. But as mem access is only working on 4K, you still have to be aware of shattering super page, because mem access can be enabled after the guest has booted. So he may have 1 GB super page, and you will have to shatter it. In the case of that, when I saw the stage 2 page tables in Xen, rather than trying to fix the code to handle super page, have decided to rework them to make each entry easy to the helper very easy to use, like getting an entry, setting an entry in the page tables. So I've reworked all the page tables. I sent an RFC recently, a few weeks ago. It's only for stage 2 page tables, so I haven't yet looked for hypervisor page tables. I'm sure there is some testing on it. I've done basic testing of my platform, but as I mentioned, break before make may be different on each processor. So, I mean, the behavior may be different on updating page tables on each processor, how it's viewed. So, it's testing on most of the platform will be really welcome. If you have any comments about the code, any concerns about the performance, on any review, it will be more than welcome. So this is the end of my talks. Is there any question? Yep.
I think you mentioned that we have SMMUs being used at the same time because we're sharing page tables is cause problems. You need to have separate page tables for the SMMUs.
So I don't know how. So you can't do break before make for page table on SMMU because the device can't write about DMA. I haven't much looked at it yet. I don't know, Mark, if you have any. Yeah. So. So when I did my testing about stage 2 page table, I've noticed that in most of the cases, the stage 2 page table are not modified at all when the guest is running. It's very either at really boot of the guest, or because they want to map like the vCPU shared info or the ground tables. But in other cases, I haven't seen many updates. Most of PV drivers are able to do copying data from the hypervisor, so you don't have to map unmap page. There might be, They might have something about DOM0, maybe, depending on the backend, but I don't know. I will say that this code is still better than what we have today, where we know that it's not running on some platform, or it may break at some point. So as we don't much have pass-through on Xen ARM today, we can think about the SLMU later on when we'll add PCI pass-through, etc. on the platform. So I know that speaking about SLMU, I know it's not related to this talk, but we may want to unshare the page table at some point, because if you use GigV3 and you map the doorbell, on the specification it clearly says that the behavior is unspecified. It's implementation defined if the processor is writing in it. So we don't want, we want the device to be able to write in the doorbell, obviously, but we don't want the guest to write in it. So that might be a case where we will want to unshare the page tables. But the question is whether we want to unshare everything on the page tables, or like having two separate sets, or having only a part of the page tables, because it costs memory on Xen also to unshare the page table. Any other question? Okay, thank you for listening.